The next relations that we're going to look at are relations called partial orders. We're first going to consider the problem of taking objects in a set and putting them in order. We're going to interpret the ordering of those objects as a relation. That will help us define both partial order and a total order. And then we're going to look at a couple examples. So let's look at putting the set containing the first 8 letters of the alphabet in alphabetical order. There are at least 2 good ways that we can express this order. The first is we can just line them up in a list. There we go. This can get a little clunky when our sets get large. If we had the whole alphabet, or even worse, if we had an infinite set of elements that we had to put in order. But we can also define a relation as a rule. So if alpha and beta are letters in the English alphabet, we say alpha is related to beta if alpha becomes at or before beta in the alphabet. So once we have this relation, we can generate the order of the letters without having to write everything down. So then the question that we might ask is, what kind of relations actually allow us to put objects in order like this? Well, let's first take a look at the properties that such relations can have. First, because we're saying that the first letter can come at or before the second letter, we allow the possibility that alpha is related to alpha for every letter alpha, which means that R is reflexive. And for the next property, let's see what happens when we choose 3 letters. So if we take these first 8 letters of the alphabet and say choose B, F, and H, we know that B is related to F because B comes before F, and we know that F comes before H, and it happens that just knowing those 2 pieces of information, we can tell that B comes before H. Otherwise, this notion of putting them in order wouldn't make any sense. But if you look at what that's saying is, if B is related to F and F is related to H, then B is related to H, well, that's just the transitive property. So R must be transitive. So at this point, all the relations for partial orders look a lot like equivalence relations. The question is, can they be symmetric? And the answer, well, is no. For instance, if I take A and D, A is related to D because A comes at or before D, but we do not have D is related to A. And if you think even for just a couple seconds, you can figure that if you have 2 different elements, the first one could come before the other, but if that's the case, you can't do that the other way around. Once you choose which one's first, you can't have them both come first. So the question is there any way that we can have alpha related to beta and beta related to alpha? Well, if alpha and beta are different, we certainly can't. But because our relationship is reflexive, we can do that when alpha is equal to beta. And in fact, that is the only situation where that can happen. So that leads us to the following definition. If R is a relation on a set A, we say that R is antisymmetric if the only way we can have both A related to B and B related to A is when A is equal to B. So now we're ready to define what a partial order is. If R is a relation on a set A, we say R is a partial order if it is reflexive, antisymmetric, and transitive. And in this case, we call A a partially ordered set, or if we want to say it slightly shorter, we can call it a poset. So if you take a look at the alphabetical order relation that we had a little while back, it actually has one more property other than the ones in the definition of a partially ordered set than might be obvious. So let's give a definition here. Let R be a relation on a set A. We say that R is connex if given any A and B in A, we either have A is related to B or B is related to A. Notice that in the alphabetical order relation, any 2 letters, one of them has to come before the other. So either A is related to B or B is related to A for any of those elements. We say that R is a total order if it is both connex and a partial order, and you might get from that part of the definition that it is possible to have a partial order but not to have it be completely connex. And we'll give an example in a little bit. So here are two examples that we can have of partial orders. So we're going to define a relation on the integers. We have A is related to B when A is less than or equal to B. So it's not hard to check that R is a partial order. Just go through the properties and see what happens there. It turns out that R is also a total order. And to prove that, I'll go ahead and tell you that one. If I have two integers, it is absolutely going to be the case that that one comes at or before the other. We may not know which one, but one of them comes before the other. And that is all you need for a relation to be connex. And so that makes R a total order. And if you want some more details about proving that it's a partial order or total order, the reading assignment that I have on Blackboard with this video will help you out with that. All right, so here's another relation that's a little bit different. Actually, similar but different. So we're going to call that relation P, and we're going to say that A is related to B under this relation P when two things happen. First of all, A is less than or equal to B, just a regular old less than or equal to, and either both A and B are even or both are odd. So for instance, 2 is related to 4 because 2 is less than or equal to 4, and 2 and 4 are both even. But 2 is not related to 5 because even though 2 is less than or equal to 5, 2 is even and 5 is odd. So let me give you a brief explanation of why P is a partial order. So every element is related to itself because, well, we know that A is either even or odd, and so both A and A, being the same thing, are either both even or both odd. That's pretty straightforward, right? They're literally the same number, so they have to be both even or both odd. And A is less than or equal to A. That's just the definition of less than or equal to. That makes it that P is reflexive because every element is related to itself. If you happen to have A is related to B and B is related to A, well, two things are true. Either A and B are both even or A and B are both odd. And it is also the case that A is less than or equal to B and B is less than or equal to A. Now, I'm going to ignore the even and odd thing here because it turns out that just knowing that A is less than or equal to B and B is less than or equal to A, we can automatically conclude that A is equal to B, just by the definition of less than or equal to. So that means that P is antisymmetric. And finally, if for the transitive property, if A is related to B and B is related to C, well, we know A and B are either both even or both odd. B and C are also both even or both odd. And since we have B in both of those statements being, and it can only either be odd or even, but not both, that tells us that A, B, and C are all three of them all odd or all even, which means that A and C are either both even or both odd. And since we have A is less than or equal to B and B is less than or equal to C, that tells us that A is less than or equal to C. So what do we know? A and C are either both even or both odd. A is less than or equal to C. That means that A is related to C, and therefore P is transitive. So it's a partial order. Now I do want to point out that this partial order is not a total order. If A is even and B is odd, they cannot be related to each other. We can't have A related to B because A and B would have to either be both even or both odd. They're not. Nor can we have B is related to A because, again, B is odd and A is even, so they can't be both odd or both even. And that tells us that P is not connex because I just found out some pairs of integers that can't be related in either direction. And that also means that P is not a total order. All right, so if you have not done so already, please read the first 2 pages of the reading Partial Orders and Partially Ordered Sets. That'll give you a little bit more details about some of the examples that we looked at in this video. And then you can work on the first set of activities, partial orders, directed graph on the PDF file included with this video.